I love being last because I have the shortest runway, so I'm going to go quickly through my slides, and then we can handle any questions. So first things first, I love these sayings. So Ari Berman, who's also with BioTeam, has the ultimate goal is to simulate your body. You know, that's the sort of long-range sci-fi looking view of where everything's heading in science. One of my favorite sayings is from Alfred Korzybski, which he's a semantics guy. The map is not the territory. And what this really means is we know what we know today. But what we know today is necessarily what it's going to be tomorrow. And so you can just imagine what it was like 100 years ago when they mapped out phrenology areas on your head, and that's how they determined certain traits. And now here we are talking about little devices sequencing an entire genome in the middle of a park or something. It's just crazy how fast it's moving. But, you know, again, that's actually quite an important statement to say. And I'm just going to walk through this example very quickly because I think the work that's happening in this particular area, in this vertical in life sciences, is just it's going to change humanity fundamentally. So one of the things that, you know, we've noticed is lots of studies are coming out based on deep dives into lots of genomic data. There was a study about schizophrenia, where, you know, 2.4 million people in the United States, just in the United States, are affected by schizophrenia. That's a lot of people. I know, relatively speaking, it's not a lot of people, but it's enough. And, you know, what can be done for them? And so there was a study between Harvard and the Broad Institute using 65,000 genomes, you know, comparing them to controls from 22 countries, and getting the data from a lot of different places that I won't list out. You can see them here, and you can get the slides afterwards. But the net of it was they were able to sort of correlate to say a number of copies of C4 gene were more frequently expected if they had a higher number of copies of that gene. And that may have been due to, and this is, you know, when I looked into this, I was just amazed because I'm not a scientist, the fact that synapses prune. I mean, who would have thought about that? Unless you're in the business and you're looking at this particular thing. And it's like, wow, so if there's too much pruning when you're young, you may have more of the protein. Ergo, you may have a higher incidence of schizophrenia. But as I said, the map, you know, and this implication could lead to drugs and therapies, and this was really based on the ability to crunch a lot of data. But referencing my map territory, you know, quote, this may be wrong. I mean, it could be down the line that there's something else out there that influences this. And when you think about the findings and discoveries in DNA today and how DNA can be impacted through environment and what does that mean and just the whole thing, there's so many ways this can go. And what that really translates into from at least my perspective is the sheer volume of data is just incredible. And we think we have a lot of data today. I get this impression this isn't a lot of data relative to, let's just say, 5 years from now or 10 years from now. And yes, there could be sophisticated compression technologies, you know, invented that allow you to store, you know, some abbreviated amount of that data. But again, assuming that the map is not the territory, you may want to keep everything just in case, right? And so what you end up with is this just massive amount of data. And most of that data is sitting in a lot of different formats, text files, it could be in a database. Adam was talking about metadata earlier about like what device did what. I mean, that could be a giant database of references to specific files. And you could have situations where there's large 600 gigabyte files in, you know, thousands of directories deep in a directory structure sitting on network attached storage, and you've got to figure out, you know, you're only working on some percentage of that in any given day. But the point being is that there is just a ton of data, and that's just today. And I think that as you know, people don't really make this connection, but think about a day where you have your autonomous vehicle, and your autonomous vehicle monitors your blood pressure as part of your insurance policy. There's something to be afraid of. But you can tie that back in. It's biometric data that can be acquired. But what people don't often think about is that there's a different side to this, and that is the computational side. You guys live it all the time. But ultimately, having all of this compute means, or having all this data means that there's so many more things you can analyze. And by being able to analyze more things and have more rounds of analysis, that means that there's far more demand for compute. And there's not too many choices about how to expand compute. My assumption in that last bullet is your institute has X number of dollars, it has this much capital, it can put this much in the data center, there's only so much network connectivity as Adam referenced, and so how much more opportunity can you take advantage of? Like, are you a node that has a lot of sequencers and you're servicing downstream institutes? That's a good place to be. If you're a downstream institute, how can you just accrue data from archives and do processing on it? So your choices are really go all in to the public cloud, increase local data center investment if you have the budget for it. These days, that's not a guarantee. You could do a mix, as Tim pointed out. You could have a fairly sophisticated orchestration environment that would allow you to take advantage of that. You could use online services such as DNA Nexus as one option. Again, assuming that the map is consistent for this point in time, that's a pretty safe approach to go for certain activities. Or you could do some mix of all of this.